session for today. So, we looked at a lot of greedy techniques and problems which can be solved by some greedy technique in the previous class. So, today we are going to discuss how you can apply. There are some problems actually in greedy algorithms which can be actually in graph algorithms, I'll say, which can be solved using greedy technique. Okay. So before we discuss any such algorithm, I would like to introduce what do I mean by a spanning tree and a minimum spanning tree. All right. So this is the topic for today. So a spanning tree is something. So suppose a graph is given to me. Okay. Suppose I have a graph. Okay. And assuming that it is connected as well as it is undirected. Okay, undirected connected graph is given to me. All right, so if I try to create a subgraph out of it, okay, this subgraph has all the vertices of the directed graph and is connected. Okay, it has all the vertices of the original graph and it is connected. Okay. So this subgraph is known as a spanning tree if this subgraph has n minus 1 edges. Okay, n minus 1 edges. Okay, so let me take an example, something like this. So if I have a graph, let's say 3 4 5 6, something like this I have. Okay, so if I want to create a spanning tree out of it, just a minute. If I want to create a spanning tree out of it, it will be nothing but you keep all the vertices of the original graph and try to use n minus 1 edges to create the spanning tree. So something like this, and let's say this, and then this, and then this. This is one of the spanning trees, okay? So those n minus 1 edges are to be taken from the edges of the original graph, okay? That is why we are saying that this is a subgraph of the original graph. That means the edges which are present in the subgraph should be, of course, present in the original graph. Okay, so this is what is known as a spanning tree. So if I look at the definition now, a spanning tree is a subgraph of a connected and undirected graph, which is a tree, of course, and is connected and connect. Sorry, not connected. Connect all the vertices together. Okay. So number of edges, if a graph has n vertices, original graph has n vertices, number of edges in the spanning tree would be n minus 1. Okay, this would be the number of edges in a spanning tree. Okay, so now based on this, let's see what is a minimum spanning tree. So minimum spanning tree is a basically a weighted connected. So right now I took this graph. This was unweighted. Unweighted means there's no weight on each edge. So by default, you can assume same weights. Like you can assume weight as 1. Okay. But now we are saying we have a weighted connected graph. So basically each edge will have like something, some number. That is called the weight of the graph. 10, 11, and 12. Something like this. Okay. So now you are given a weighted, undirected, connected graph. Okay, that is what we mean by weighted, undirected, and connected graph. Okay, so minimum spanning tree is spanning tree of a weighted, directed, connected graph. One moment. Yeah, weighted, directed, connected graph with weight less than or equal to weight of every other spanning tree. Okay, so let me just before I move to this point, let me just emphasize on this. So let's say you have this graph with you. All right, this graph is given. Let me try and draw two spanning trees. Okay, two spanning trees. I'll not worry about minimum spanning tree right now. I'll worry about two spanning trees. So I want to draw two spanning trees. Let's say first one is 1, 2, 3, 4, 5, and 6. So let me include this 10, 9, let's say this is 8, and this is 7. Okay, this is one spanning tree. Let's say this is the other one 2, 3, 6, 4, and 5. And let's say you include this 10, 9, then 8, then 7, and then let's say this is 9. Okay, right? Now, see, first of all, how to find weight of a spanning tree? Weight of a spanning tree is whatever edges you have included in that particular spanning tree, sum up the weights of all the edges. Okay, sum up the weights of all the edges. So if you sum up the weights over here, it will be 22, 9 is 31, then 39, and then 46. Correct? So the sum of all the weights of this spanning tree is 46. Sum of all the edges, weights of the edges. Okay, now if you try and sum up this will be 10, 19, 9. So this is 19, and then 9 would be 28, then 15 would be 28, 38, and 43. So this is giving me as 43. Okay, weight of weight in this case is 43. So basically, this spanning tree has less weight than this spanning tree. Okay, so now what they're saying is minimum spanning tree is the spanning tree which has least weight among all possible spanning tree for a particular connected undirected weighted graph. Is this point clear to everyone? What do I mean by spanning tree and what do I mean by minimum spanning tree? Everyone? All right, okay. So now, given that this is the condition, so weight of a spanning tree is the sum of weights given to each edge of the spanning tree. So basically, whatever weight you give to each edge of the spanning tree, you sum up all those weights, and then whatever final answer that you get, that is the weight of the spanning tree. Okay, this is how you can calculate weight of any given spanning tree. All right, so this is the basic. Now, what we have is we have some greedy technique by which actually we can find a minimum spanning tree. Okay, so before we go on to minimum spanning tree, this is a small problem for you. Just tell me which of the following graphs, these are the graphs, which of the following are spanning trees and which are not. Do it. Okay, so let's see A now. So in A, what you have is you have four vertices, okay, and then four edges, four edges. So, but I need what? Three edges, correct? Three edges, and it is connected, but it should have three edges. So, A is not a spanning tree. Okay. How about B? B, we have 1, 2, 3, 4, 5, five vertices, and 1, 2, 3, and 4 edges, and of course, it is connected as well. Okay. It is also it is a spanning tree. Okay, it is a spanning tree, reason being it is connected and it satisfies our criteria. Now if you say take C as example, so this 1 2 3 4 5 6 6 vertices, and how many edges? 1 2 3 4 5 6 edges. So of course this is not a spanning tree. Okay, now can I conclude from this that a spanning tree can never have cycles? Yeah, because I'm saying it should have n minus 1 edges and it should be connected. Remember one thing, if you take any graph, okay, and if you want a cycle now, you should have at least n edges. So these small things they can ask. You should have at least n edges to create a cycle if you have n vertices in a graph. Alright, so this is an important point. So please make sure that you note this down. Okay. Alright. Okay. Now this is the same point I repeated. A spanning tree with contain which sorry this is which contains exactly v minus 1 edges will contain exactly v minus 1 edges if there are v vertices in the respective graph. Okay. Again, so now we talk about MST. Now I hope definition of a spanning tree is clear. Okay, and given a graph, you may have multiple spanning trees. Okay, multiple spanning trees with multiple weights, with multiple total weights. Okay, so now there are two algorithms. In fact, I'll say there are two greedy algorithms. Okay, which can help you find minimum spanning tree for any given graph. Okay, minimum spanning tree for any given graph, there are two algorithms. So we would like to first check out what is Prim's algorithm. Okay. So I'll go through Prim's algorithm using an example, and then we'll see the actual algorithm which is written in the slides. Let me say I have this graph with me, 4 and 5. This, this, and this. Okay. Weights I'm assigning 5, 10, 3, 7, 8, and 4. Okay. All right. So I want to, what I want to do here is I want to find the minimum spanning tree from this question. Okay. From this question. So how you'll do it is simple thing. So what Kruskal says is, okay, since all the vertices are required in the minimum spanning tree, what you do is you sort the edges in ascending order. As simple as that. Okay, you sort the edges in ascending order. Okay, once you sort the edges in ascending order, take minimum weight starting from the minimum weight of the edge, take that. Okay, include that. Okay, in the final MST. Okay, keep adding weights. Okay, keep adding edges. Okay, you will add an edge only if the edge does not create any cycle. Clear? You will add an edge only if the edge does not create any cycle. This is the condition. Okay, so what you do is after one next minimum weight is what, let's say this is 2. Okay, next minimum weight is what, from 2 to 3. So after second iteration of Kruskal's algorithm, this is the condition. Okay, after that you will add weight 3, and which is what, 4 to 5. Sorry, 4 to 5. 3 is added. All right, now I want to add 4. But what is happening is, okay, I can add 4 here and I am actually done. Okay, the edges that I took, 1, 2, 3, 4, actually they did not create any cycle, which is why I am completely safe here, and this is the minimum spanning tree required. Okay, now do you have any intuition why this algorithm will always give you the right answer? How this will give you the minimum spanning tree always? Any intuition behind this? Yes. Right. So it is including all minimum edges. So Sanjeev, this will not be true always. Okay. So first of all, is this example clear? I'll modify the example, modify the question. So please tell me if this is clear or not. All right. Yeah. I'll tell you why it will not be true. Okay, because I'll tell you one more thing. Actually, today I was going through all the 6 7 years questions, and from greedy algorithm, in fact, there's only single question from the algorithms that we did in the previous class, and you can say at least 10 questions were there in the past 7 years from minimum spanning tree. Just this topic, just today's class, whatever we'll see. Okay, 10 questions, and in fact in 2022 questions have been asked for 2 marks each from spanning trees and minimum spanning trees. Okay, this these like this is the level of importance that gate gives to spanning trees, I can tell you definitely. Okay, so we'll see this now. Assume I make this weight, let me make this weight as, wait, I need to think 1 minute. Let's say this is 10 only. This was what, 10? This was 10, and this is what, 4, correct? Okay, so okay, let me take another graph. I have something else in mind. Okay, please draw the minimum spanning tree according to Kruskal algorithm for this graph now. Yeah, try for this algorithm. Try for this graph. Draw the spanning tree according to Kruskal. Again, take the edges in sorted order, okay, one by one. And if you include a particular edge, okay, and if any cycle is created because of that edge, then do not include that edge. If no cycle is created, then you are safe. Okay, do it. Once you are done, please write it down in the chat. All right. Now if you see this, first I'll take 1. That means I'll connect this. I get 1 to 4. This is the least. Then is 2. 1 2 3. Okay, this is the second least. Then you have 3, so I'll connect this is the third least. Now if I try to add 4, see, I'll create a cycle, so I'll reject 4. I try to add 5, I'll again get a cycle, I try to reject 5. Now I would try to create 100. Okay, so now see, between 3 to 5 there is only single edge. Okay, I don't have any option but to include this edge in the MST. Is this example clear to everyone? I'll write a statement. Please tell me if this is true or not. True or false? Heaviest edge of a graph can never be included in the MST of G. Graph G, of course. Correct? This is false. And the reason is in front of you. This is the example for this. Alright? And I'll tell you that this is one of the gate statement that had come previously. Okay? So now I hope little bit things are clear about how an MST is created out of a Kruskal algorithm. Yeah. Okay, so let's now go through the algorithm ones. Okay, they are saying sort all the edges in non-decreasing order of their weights. Then pick up the smallest edge, check it forms a cycle or not with the spanning tree. Okay, formed so far. If cycle is not formed, include the edge, else discard it. As simple as that. Right? Now repeat step 2 until v minus 1 edges are there. Okay? As soon as v minus 1 edges are there, you can actually stop. Okay? So the greedy choice here is to pick the smallest weight that does not cause a cycle in the already constructed MST. Okay? So another way to say this is what? If you would have observed in the example, okay, so every time I was adding an edge, okay, I was trying to add a new vertex to the existing graph. Is this correct or not? At least one vertex to the existing graph. With every additional edge you're trying to add at least one additional vertex to the graph. Correct. So this is another way. If you don't want to, check out the cycle concept, this is another way to uh, create the minimum spanning tree. Okay. With every edge, you should add at least one new vertex to the graph. If with an edge you are not adding any vertex to the graph, that means your edge may contain a cycle. All right. So this is the Kruskal algorithm. Please tell me if you have anyone has any doubt in Kruskal algorithm. Actually, this is one of the easiest one. Okay. So if no one has any doubt, please solve this first and second. Both the questions. Try. You have to give me the minimum spanning tree using Kruskal's algorithm in both of them. First and second both. Try and then write it in the chat once you complete. Everyone completed? Anyone who needs more time? Okay. All right. So I hope everyone has completed. So let's see the solution for this. Okay. So I'll not. I'll try to explain the solution within this graph only. Okay. So see. Now the thing in Kruskal is you can start from anywhere. It doesn't have to be the there's nothing like source or sink in this, or the source or the destination, something like that. Okay, so you start with the edge which has minimum weight. So you'll start with this. Okay, this is your first edge. Now after this you'll take up two. Now there are two twos. Okay, so you'll take up this, you'll take up this. Okay, this is done. Till now my graph, uh, till now there are no cycles, so I'm safe. Okay, then after two I have, after 2 I have a 4. So this connection comes in, and still I do not have any cycle. Again this connection comes in, I do not have any cycle. After 4, next number is what? Do I have 5? No, I think I have a 6 then, right? So 6 is what? Now see, when you add 6, after adding 6, there is a cycle which is coming, right? See, there is a cycle which is coming, so I will not add 6. Okay, 6 is rejected. After that, 7. So if you add 7, now after adding 7 also a cycle is coming, see. You see the cycle, correct? And you see that 8 and 7 are already part of the MST. So since no new vertex is added when you are adding the edge with weight 7, hence the edge will be discarded. Okay. Now 7 is 2 and 3 also. Now 3 is added. 3 is the new one added. Yes. So this is all right. Okay. Next is what? 8. So now if you add 8, what will happen is, do we have a cycle if we add 8? Yes or no? All right. So I don't think we have a cycle over here. See, 8 will be added. Okay. But now see that point where what I mentioned becomes invalid over here. 1 was part of the MST, 2 was also part of the MST. But what we are doing is you are connecting 1 and 2. Okay. Now 1 and 2 becomes connected. Previously 0 and 1 was separate and the remaining part was separate. So those two were disconnected. Okay. So now 1 and 2 are connected. So again we don't have a cycle. We are good to go. Next is what? After 8 you have what? 9. So you add 9 and this is it. Okay. Now is there any edge left? So let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices are there. So I should have 8 edges. 1, 2, 3, 4, 5, 6, 7, 8. Yes, I have 8 edges. So this is the MST. Everyone, is this clear? I'm not drawing the MST. It'll take a lot of time. Is this clear to everyone? Yes or no? The first one. All right. Okay, so let's see the second one. I think this vertex is 9. Okay, so now you're going to add what? So, okay, 2 is there. So I'll start with 2. I connect these two. Okay, then 14. Then I'll have a 6 maybe. Yeah, so 6 connected. This also connected. No cycle formed till now. Okay, and after that I have a 7. Fine. So I'll connect a 7. Okay, no cycle formed till now also. Then I have a 8. So 8 also connected, no cycle formed till now. Okay, then you have a, I don't have a 9. I do have a 10 though. So let's connect 10. Okay, this is also connected. So after that I have 11. Now see, if I connect 11, what is going to happen is I will, I think, get a cycle. Yeah. So if I connect 11, see, I'm getting this triangle as the cycle. So I will not do it. Okay, 11 is discarded. And then we have 14, I think. Yeah. 14 is also discarded. I'll also get a cycle using 14. See, this is the cycle that I'm getting, right? 14 is again discarded. How about 23 now? Yeah, 23 can be added. Okay. Now 23 is added. So 26 cannot be added because this will give me a 3-length cycle. So 26 is discarded. After that, finally 30 would be added. Okay. See, again in this case, I'm adding the heaviest edge in the MST. Okay. 30 would be added. Okay. So the sum here, how many vertices? I think 9 vertices. Edges are 1, 2, 3, 4, 5, 6, 7, 8. 8 edges, 9 vertices. Yes. So according to Kruskal algorithm, this is the minimum spanning tree of the second question. Second question also clear to all of you? All right. So it might seem that this is very easy and all, but we are just starting. Okay. This is the build up. So now next question is how to find the time complexity. Would you guys like to solve time complexity? Just give me a rough idea. What will be the time complexity for Kruskal's algorithm? Sanjeev, can you explain your answer? How did you get order E log E? Yes, correct. Yes, you'll sort them. Correct. That will be, and you're sorting the edges. So that will be order E log E. And anywhere else, do we want to spend any time? Everyone, please try it. Anyone else? See, algorithm is in front of you. See, this is the algorithm. This is the algorithm, right? Yeah, adding the vertices. See, I'll tell you the time complexity. Okay, see, so there are two aspects of the time complexity. One is, first is sort edges, right? So when you sort edges, and if there are E edges, so that will take order E log E time, correct? Now the second aspect is when you're adding an edge, okay, adding an edge to the current MST, You're checking for a cycle, right? Right? Now you guys remember few things that are taught in data structure on algorithms which could detect a cycle. I don't need the length of the cycle. I just need to know whether if I add this edge in the particular MST, can I have a cycle or not? Please tell me which algorithms did we study to check this out. Yes, we studied BFS, we studied BFS and DFS, right? Breadth first search and depth first search. So, students who have not covered data structures, so these are the two algorithms. In short, you can just understand that these two algorithms will help you detect whether there is a cycle in the current graph or not. Okay. So basically these two algorithms. Now, what was the time complexity? Order V plus E. Everyone? Yes. This was the time complexity for either BFS or DFS. So basically you are doing this for what? Doing this for every edge. So the time complexity becomes what? V into E or E into E you can say, right? E into E, correct? So if you use BFS or DFS to find the cycle, the time complexity becomes E log E plus E into V plus E. Okay, this is the time complexity for Kruskal's algorithm if you're using BFS and DFS or DFS to find the cycle. Is this time complexity clear to all of you? Yes or no? Because you're doing that for every edge, right? The worst cases you will check all the edges, correct? If you want to include the heaviest edge, you have to check all the edges. So that's why this is E. Alright, now I'll tell you another way. Okay, so there is an algorithm known as union and find. Okay, I think it is known as find and union. Union find algorithm. Okay, so this detects a cycle in order log v time. Okay, so if you try and use this algorithm detect a cycle, this will be done in order log v time. And now if I use this algorithm instead of BFS DFS to find or to detect my cycle, so this will be order E log E plus E log V now. Okay, so now the algorithm the time complexity becomes order of E E log E. Is this clear to everyone? Okay, so we'll not go in detail for a union find algorithm. This is out of scope of if I say with respect to gate. All you have to understand is this helps us detect a cycle in order log v time. And well, if you're interested, if you just want to know, you can study this algorithm from Geeks for Geeks or somewhere from the internet. Okay, but this is a little complicated, so we'll not be going into that. Okay. So the time complexity for Kruskal's algorithm becomes E log E if you're using union find algorithm to actually detect the cycle. Is this clear to everyone? Good to go? Yeah? Alright, so this is what I've just discussed. Okay. If you use find and union operations and all, this becomes order E log V. And this is the final, this is the total complexity which I've discussed. Now see, this whatever I've written over here is nothing but when we have a complete graph. If you remember in complete graph, every vertex is connected to n minus 1 vertices, correct? So number of edges that we'll have in a complete graph will be n into n minus 1. Okay, Number of edges in a complete graph will be n into n minus 1, sorry, by 2. N into n minus 1 by 2. This will be the number of edges. Okay, so this is by 2. So now, worst case time complexity for in case of Kruskal algorithm, now if you put E as order of V square, so this will give you order of n square log n. Is this clear to all of you? This is the worst case time complexity in case of uh, a complete graph. All right, so next thing we are going to look at is, now time complexity is done. You know how the how Kruskal algorithm runs and gives you an MST. Now we'll look at Prim's algorithm. Okay, so Prim's algorithm also gives you output as a minimum spanning tree. Okay, the output of Prim's algorithm is also a minimum spanning tree. Okay, but the greedy technique here is having a little change. Okay, and that little change is to select the minimum weighted edge among all the edges for the vertex in consideration. So what do I mean by a vertex in consideration? I'll tell you using an example. Okay, so there's a slight difference. Please check. Let's say I have this again, a graph with me. Okay, so 1, 5, 7, 8, 9, 10. All right. So now let's say you start with 1. Okay, let's say you start with 1. You continue, you add this edge, right? Because what you'll do is, for 1 you will check all the edges which are connected through 1. Okay, and you'll take the minimum from them. Okay, you'll take the minimum from them. So you have taken 1 now. Okay, you have taken 1 now. Now what you have to do is, you have to consider the previous edges also. Or let me just explain the dry run in this form. Just wait. That will be easy. 4 and 5. Let's say the same widths, 1, and this was 5. Connection. This is, let's say, 6, 7, 8, 10, and 9. Okay. Now what you'll do is, if you want to start with 1, you assign the value 0 to 1. Okay. You assign the value 0. Okay. For this particular node. And all of them you assign as infinity. Okay, please, this is important because I'll build up the Dijkstra's algorithm on this concept only. Okay, so what you do is simple. If your current weight, current edge weight is less than the value of this edge, that means if, okay, so let me call, just wait on. So edge u to v is in consideration. Okay, this edge is in consideration. If weight of u, and you have to consider weight of v. Okay, and the third thing you have to consider is weight of edge u to v. Okay, weight is this node, this value that is there, this is I'm considering as weight. Okay, so this, if this guy this weight is greater than this weight. Okay, so you modify your weight of the node as the weight of the edge. Is this point clear? If weight of the node is greater than the weight of the edge, then you say the weight of the node is equal to weight of the edge. Is this point clear to everyone? Weight of the node is equal to weight of the edge. Right? So something like this. Something like this between 0 to 1. Okay? 1 to 2, there is an edge 1. 1 is in consideration. So what you do is you modify the weight since the value is infinity. For node 2, the value is infinity. So you modify this weight to 1. Alright? You modify this weight to 1. And similarly for 3, what you'll do is you'll modify this to 5. Alright? So once you do this modification, whichever weight or whichever node has the least value, that will be selected for the MST. Okay, so I'm going to draw the MST now, and I'm going to update the values. All right, so this is what between 1 and 2, this node will be added, and this will be the part of the final MST. All right, let's do it again. Okay, so node 2 is added. We are done with 2. All right, this node is completed. We have 3 nodes left. Okay, now you are at 2. Now 2 is the node in consideration. Now what you'll do is you will check all the adjacent node which have not been visited from node 2. Okay, so which the nodes which have not been visited is what? 3 and 4. Okay, so now if you check what is the edge linking node 2 and 3, edge is 6. Okay, is 6 greater than 5? Yes, right. Or you can say 5 is greater than 6. No. So you keep 5 as it is and you will not consider 6. Alright. So basically these values that the nodes are storing, they store the value of the previous edge visited. Okay. 5, 1 and 5 were already visited. So they store this value 5. Alright. And now 4. For 4, between 2 and 4, I have a link 7, correct? So now this link, this value 7 is less than infinity, right? So you modify this to 7. Alright. Now you check whichever value, the nodes which are not visited among them, which is the minimum value. So 5, infinity and 7. 3 values are there. 5 is the minimum. So you add this node. Now this is the part of the MST. Okay, so let's repeat this again. So now you are at node 3. Okay, so from 3, what all edges are there? From 3 there are what? Let's say this node is 6. Okay, let's say this node is 6. I just want to implement something. Okay, so from 3, which all nodes are not visited? 4 is not visited and 5 is not visited. Okay, so from 3 there is a connection to 4 and the weight is 6. Now 6 is less than 7. That means I have a lower cost. So I will replace this by 6 now. Is this replacement clear to everyone? Yeah? Everyone please respond. Is this clear? Yes or no? Alright. So now from 3 I have to again consider all the adjacent vertices which are not visited. Okay, so 5 is also not visited, so 10 is the link, so I'll have a 10 over here. Okay, so that's it. Now out of those 6 and 10, only 4 and 5 are the nodes which are not visited. So out of 6 and 10, which is the minimum? 6 is minimum. Okay, so you will actually mark this link. All right, this will be part of the MST. Now what happens is 6 is done. Now we are at 4. So out of 4, the link is, there's only one node which is left, which is 9. Okay, and you see that the previous value for node 5 is what? 10. So and the new edge has value 9, which is lesser than the previous value. So you do a replacement. Okay, and now this is the last value. So this is the MST using Prim's algorithm. Is this MST clear to everyone? let's try another problem on this. Okay, let me give you another problem. Before I discuss the algorithm, let me give you another problem. Okay, now do it. You can start from any vertex, okay? That's the good thing about prims. You can start from any vertex you like because every vertex will be included in the MST. Try this out. Anyone who needs some more time? Anyone who needs more time? All right, okay. So now let's see this problem. So again, let me start with what? Let me take something interesting. Let me start with 3. Okay. You ultimately you'll get the same MST only. Okay. You don't have to worry. So with 3, how many people are connected? I'll say the. Let me just take the values now in blue. This is 0, infinity, 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 and infinity. This is the initialization that will do. After that, 0 between 3 and 5, there is an edge with link 4, so this becomes 4. Between 3 and 6, there is an edge 2, so this becomes 2. Between 3 and 2, there is an edge, this becomes 1. The weight of the edge is 1. Between 3 and 4, there is an edge 2, so this becomes 2. And what? And what? And that's it. 4 edges, 4 modifications. Now you have to find the minimum out of these all numbers. So you have 5 vertices, 2, infinity, 1, 2, and 4. Minimum is 1. So you basically make this connection. Okay. So make this connection, and this is the first vertex. Okay. This is the weight 1. Now from 2 you start taking adjacent edges. Okay. So from 2, first one is 1. Okay. So see, previously the value is 2. For no, vertex 4, the value is 2. And now From node 2, if I connect 4 now, it is with the weight 1. So this is modified to 1 now. So 2, this is already done. Okay. And then another one is 3. Okay. But see, now this 2 is there, which is actually less than 3 already. So I'll not make any changes to this 2. This 2 is fine for me. Okay. Then you have from 2, again 1 is connected with a weight 2. So I'll modify this to 2. That's it. We have considered all of them. Yeah. So now which is the minimum? This is coming out to be the minimum. Okay. So 4 is connected again. So now from 4, I have what? I have 2 connected, which I have completed, 3 connected, which is completed. I have 5 connected. So this 5, I just write the vertices. Okay, yeah. So this 5 is connected, but this is connected through an edge weight 6, and the value is 4. So 4 is already less than this, so we are good to go. Okay, we don't have to change or modify the node value of 5. Okay, so now what you do is whatever values are remaining, okay, 4 is also done. Okay, now whatever things are remaining, 2, 2, and 4. So pick up any one. So let's say we pick up this 2. Okay, we pick up this 2. Now this is added, and now from 1 all I have connection is to 6, and 6 is with a weight 5. Okay, 6 is with a weight 5. Then what happens is the value of node vertex 6 will not modify, and it will remain 2, and that's it. So 1 is also done. Now remaining values are what? For node 5 and node 6, these are two to be added. So now this is 2, and then I'll add this guy. Okay, so now this is added, and everything connected from 6 is already done, so 6 is done, and finally this is added. Yes, so this is the given MST. Is this clear to everyone? Everyone? It's little complicated if I compare this to Kruskal's, okay? But Dijkstra's is actually based on this concept, so I don't want to. I just want to teach one thing, and we want to, further utilize it. All right? Okay, so now one difference that any one of you can tell me between Kruskal and Prims. Before I go into the notes and all, please tell me one difference between Kruskal and Prims. Or if I may ask, which one is better? Do you want to comment on this? Which one is better? Yeah, you can say that, Sanjeev, but there is actually one of very important difference. Prims uses any edge, and Kruskal. See, we'll compare the time complexity as well. But when very important difference is that in Prim's algorithm, na, you always, always have a connected MST. Okay, that means whatever MST we have right now, that MST will always be connected. This is not true in Kruskal's. In Kruskal's, you may have a disconnected graph in the middle, disconnected MST in the middle. Is this point clear to everyone? This is an important point. This is an important difference between Kruskal and Prim's. Okay. So if you cannot have, if the situation does not allow you to have a disconnected graph, there is no way you can implement Kruskal's algorithm. Okay. Time complexity wise, once I discuss now, then we'll comment. I should have asked you which one is better. I should have asked you once I discuss time complexity for Prims. Okay. So I'll ask you that question. But this is the important difference between Prims and Kruskal. Okay. Prim's algorithm will always have a connected MST. Wherever it is running, after every iteration, it will have a connected MST or a connected subgraph, you can say. But in Kruskal, you may have a disconnected subgraph in the middle at some point, okay? But finally, both of them will give you the same MST, okay? The difference, the output difference will not be there. Only thing is intermediate differences will be there. So let's study the algorithm now. So this we saw. Now the next thing is create a set that keeps track of vertices which are already included in the MST. Okay. So this is easy to create. Basically, they are saying create a visited array. Correct? A visited array. Simple as that. Okay. Then assign a key value to all the vertices in the input graph. Okay. Initialize all values to infinite and assign 0 to the value from which you are starting. Okay. Only that vertex will be assigned value 0. All other vertices will be assigned value infinity. This we saw. Okay. So after that, while the set does not include all vertices, that means this particular set does not have, like visited array does not have all the vertices. Pick a vertex u which is not there in the set and has the minimum key value. Okay. So those key values you maintain, right? Those key values you maintain for all the vertices, and you pick the minimum from all the values for a vertex which is not yet included in this particular set. Okay. And you have to include that particular vertex. Let's say that vertex is u. So you have to include that particular vertex in your set. Okay. And then you have to update. Now this is the update part. Okay. Now update key value of all the adjacent vertices of u, because only those vertices, the adjacent vertices will get affected. Okay. To update the key value, iterate through all the vertices. Okay. Iterate through all the vertices for adjacent vertices, vertex v, if weight of u comma, if the weight of the edge is less than the previous key value, then update the key value to the current weight or the new weight. Okay. Otherwise you leave it as it is. Okay. Otherwise you leave it as it is. This is what we saw in the algorithm. Correct? Everyone clear on this? Okay. So this is again an example that I've demonstrated in the notes. Okay. So suppose this is the graph given to you. So this I think you can read by yourself. This example is there trying to explain how the this Prim's algorithm works and how this graph is created. Okay. So I'll not go through the example over here. The same way we solved these questions, right? So now what we'll do is we'll try to. I think I have few questions for you. Yeah. So those two questions which we solved for Kruskal, now try those questions using Prims. Okay. Try those questions using Prims. Please, everyone, try to solve these two questions using Prim's algorithm. All right, anyone who needs more time to solve this? Anyone? All right. So yeah, this is again, you get the same MST as Kruskal. Only thing is, I want you to, get familiarized with the process, with the algorithm itself, so you don't have to remember. Okay. So we can start anywhere. Let's start from zero. Okay. So for zero, the value will be zero, and these guys will be infinity. Okay. All right. Okay. So this guy will be updated to 4. I'll quickly solve this. Alright. So please tell me if this is fast or not. Okay. I'll quickly solve this. This is 8. Okay. Now you select this guy. This will be part of the MST. Fine. Now from 1, adjacent people are what? 2. This becomes 8. And this is 11. So this 8 is less than 11. So I'm fine over here. And then that's it. So now 8 and 8. So you can select anyone. Let's select this guy. Okay. Now this is the part of MST. Now from 7 we have, okay, this is also infinity. Sorry, I forgot this one in the middle. Yeah. So this will be 7. All right. This will be 1. And this one is already completed. Yeah, 3 edges and all 3 are taken care of. Okay. So now I think 1, 7, 8, infinity, infinity, infinity. 1 is the least. Okay. 1 is the least. So this is selected. Now from here, what you'll do is you'll basically this is selected. Now you are at 6. So now see, 8 is actually connected to 6 is actually connected to 8 using the edge which has weight 6, and the value node key value of this vertex 8 is 7. So I can modify this to 6 and this to 2. Okay, that's it. So now this will be part of MST. Okay, and after that this becomes 10, this becomes 14, and what, this is 4 and this is 8. So now this becomes 4. All right, this becomes now 4. So yeah, previous one is already completed. Now 4, 14, 10 and 2. Okay, 2 is also done. So 4, 14, 10 and 6. So I'll complete 4 now. Okay, so this is the part of the MST. Now this is also done. So from 2 here, now see there is an edge between 8, and now this 6 will modify to 2. Okay, so a lot of modifications for node 8. This will be 2, and then this will be 7. See, out of 14 I'll say 7. Alright, okay, done. Then 2 is connected to 1, which is already completed. So now 2 and then 7, then 10. 2, 7, 10. 2 is the minimum. So I'll select this guy. Okay. Now if you see 8, the adjacent vertices to 8, all of them are completed. So I don't have to do anything. Then I'll select 7. So 7 is selected. Okay. So that means what? 3 is done. Now from 3, 14 is done, and all you have is 4. So this is 9 now, because 3 and 4 is connected by a edge 9. So better value is 9 for vertex 4, and then this is the guy. Is this clear? Now please compare this solution with the solution we got for the same graph using Kruskal. Please compare it. Are you able to get the same solution as Kruskal's for the first one? Everyone? All right. So, okay. So I hope this is clear to everyone. So I'll quickly discuss the second one also. For second one, let me start with 5. So infinity, 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 infinity. Wait, let me just I'll rub the first one, okay? It becomes more clear. I have more space now. Infinity, 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 infinity. This infinity, infinity, and infinity. All right. So let me start with 5 now. So with 5, you have the first vertex. Just compare, just a minute. Yeah. Now compare them. So this will be 2. Okay. This will be 14. This will be 11. This is just direct. This is 6 and this is 23. All right. Minimum is 2. I'll connect these two. So from 6, there is only one edge which is to this. So this will be 6. So 6, 14, 11, 6, 23. Minimum is 6. You can take up anyone if you want this or this, anyone. Let's take this now. Okay. So this is 6. Now from 3 I have only one more connection to 4, which is the weight is 26 and the value key value at node 4 is what, 23. So I'll not change that. Okay. Now from the remaining vertices 23, 11, 14 and 6. 6 is the minimum. So I'll connect this edge as well. Okay. Now you connected this. Now you will see 7. So 7, this is connected, this becomes 30. This connected, this becomes 7. Now see, 7 to 2 is connected by an edge of weight 8. Okay. So now 2's value is 11. So I'll modify this to 8 and basically I'm done. Okay. So after 7, the minimum value will be 30 and then 7, 8, 6, 6 is done 23. Yeah. So 7 is the minimum. I'll add this edge. Okay. So after this edge, one adjacent is to 2 using an edge weight of 9. Okay. So now 9 is already greater than 8. So we'll not do anything to 8. Now the next I think would be 8. Okay. And now if you see, this 8 is what? This 2 is connected to 8 using a edge of 10. Okay. So this now is modified to 10. Alright. This is a better one. And the second edge is connected to 5, which we don't really have to care about. So this is the next edge that you'll add. Okay. This is 10 and we have 30 and 23. These two nodes are only left. Okay. So 8 is not adding any new vertex. We don't have to really worry about the edges which are connected to 8. Next is 23. So you'll add this guy. Okay. And then you'll have 30 in the MST. So please check for this solution. Are you getting the same MST what we got in Kruskal? Please everyone check the solution in Kruskal. Yeah. So this is the MST using Prim's algorithm. Only thing is every time you will always get a connected MST. After every iteration it is connected. In Kruskal you may get a disconnected one. All right. So I hope this example was clear to everyone. So now I want you see we have done two examples. In fact, I did one example I did, one you did, and these two. We have done 4 examples now. Now, can you help me find the time complexity for this? Can you help me find the time complexity for this? Same. Are you sure? Sanjeev, are you sure? Same. Think it, na? Think it. See, I did all these examples just to make sure that you remember the algorithm. Now just try and run it in your head. First thing is, of course, sorting is not there, na? We are not sorting anything, correct? We are choosing minimum. Choosing minimum, not after sorting. You're not sorting all the edges in any order. Everyone, Aditi, Neha, Kajol, please try this out. Okay, let me assume that you okay. Do you guys know what is the difference between adjacency matrix and adjacency list? Anyone has any idea? Feel free to say no. Okay. So let me just explain you. When we talk about graphs, na, in graphs there is two kinds of representation which are possible. Okay. One is adjacency matrix and the second is adjacency list. Okay. So see how these two go. So adjacency matrix is what you'll do is you'll put the vertices over here, okay, and over here. So rows and columns are nothing but vertices, okay, and each of this value inside this matrix is nothing but and the weight of the edge which is connecting those two vertices, okay, weight of the edge connecting those two vertices. All right. So basically, I want to say is if you're using adjacency matrix, as one of the to retrieve your values, this will actually have order of v square entries. Okay. Now adjacency list is what? You have a 2D list, okay, in which this is nothing but the vertex. Okay, these are the vertices. Okay, let's say 2, vertex 3, and so on. And these are of course connected to each other so that you'll have a continuous thing. And one will have those many all the adjacent vertices which are connected to one will be attached to on the right hand side of one. Okay, so if I have 2 and if I have 4 and 5 over here, that means one has a direct edge with 4 and one has a direct edge with 5. Similarly for 2, let's say 2 is 6, so 2 only has a direct edge with 6. So 3 has maybe 1 and 2. So you can say 3 has a direct edge with 1 and 3 has a direct edge with 2. This is called adjacency list. Is this clear? So now can you tell me which representation is better? Yeah, see, list is better in the case when you have less number of edges. Okay, because let's say if you have a connected graph with only v minus 1 edges. Okay, let's take a spanning tree. So in that case, what will happen now? Lot of entries inside the matrix will be nothing but 0. Okay, that means there is no edge present between those two vertices. So in that case, making it a linked list or an adjacency list would be better. Okay, but if your number of edges is nothing but order of v square, then this will be better. Okay, this will be better since in this 2D form, random access is possible. It's again an array, na 2D array. So in this, random access is possible, which is why this will be better. All right. So these are the two representations. Okay. So what I was saying is, let's say you want to use adjacency list. You want to, let's say you want to use adjacency matrix to represent this graph, given graph. Then what is the time complexity? V square. Okay. See, so in this thing, there are two parts. Please understand, everyone. This is important. Okay, time complexity for prims. If I use adjacency matrix, okay, there are two components. The first component is CSE. Always, you're checking one edge twice. Correct? Every edge is checked twice, right? Because whenever that edge, see, if you see this example, once I came to 7, I checked 1, right? Next, so basically I checked this edge 1 7. Okay, then when I came to 1, I again checked whether I considered edge 1 to 7 or not. So every time I land up at these things, I will consider that whether I've considered that particular edge or not, and every time I'll do it twice. So that means for every edge you're doing it twice. So that means 2e times of 2e times is the total number when you're checking to update the key pair value. Yeah, to update key value of nodes, right? This is the one task. And the second task is what? See, every time you modify your key values, okay, after that you're running and maybe a linear search to identify or yeah, a linear search to identify which is the minimum value. Because remember, that is not sorted as of now. Why that is not sorted? Because the values of all the nodes, they keep on changing, they keep on modifying as and when you visit more nodes. Correct? So basically, what you are doing is when you are at the first node, you want to check for v minus 1 nodes, which is minimum. When you are at the second node, you want to check for v minus 2. When you are at the third node, you want to check for v minus 3, and so on. You'll check till the last one. Okay? So this gives you v into v minus 1 by 2, which is nothing but order of v square. Okay? So the time complexity here in this algorithm is actually order of e plus v square. Okay, but this is if you try and use adjacency matrix. All right, so now this is the time complexity. First is trying to check all adjacent vertices, adjacent edges of the vertex in consideration and update the key value pair. Okay, and this is done for all the edges twice, and that I have already discussed. And then finding minimum key among vertices yet to be discovered. All right. So this is the time complexity. Is this is clear to everyone? Using adjacency matrix, what we'll get? So now next thing is, can I do better than that? Because see, v square is fixed. That's the problem. So in this is, if the input graph is represented using adjacency list, then the time complexity for Prim's algorithm is order of e into log v. Okay, and this is with the help of a binary heap. Okay, so more on this we'll see when we see Dijkstra's algorithm. Okay, I've written the algorithm which will give you order of e log v over there. All right, so this will be order of e log v. Well, this will be better if your number of edges are less. Okay, this will be better if your number of edges are less. All right, so do you want a hint of what will happen over here? Or we'll see it in Dijkstra's. Dijkstra's, when I tell you the algorithm, na, this thing will also be clear. Okay? Because really in Dijkstra's only the update equation changes. Prim's algorithm and Dijkstra's are same. Only thing is update equation is different in Dijkstra's and Prim's. That's it. Okay, so any doubts to anyone in Prim's algorithm? Yes, we are trying to find the minimum, correct? So you're using a min heap, binary min heap for that. And in that min heap, you actually have your vertices, and you're doing it for all the edges one by one. Edges will be because you are trying to update the values of vertices of the nodes of the vertices based on edges. Now, yeah, that is why we have log v there. See, the Sanjeev, the logic is simple. If you want to understand, you will build a min heap with v vertices, okay, and in that two things are there. One is the node number, okay, which node number we have, and the key value for that node. These two values will be stored in every node of the min heap. Okay, then what you do is for every edge you need to update this key value, right? So first is you try to find whether that edge is in min heap or not. If you found that edge, then you try to update this value. Okay, check the value and update. Okay, and out of those edges, out of those vertices, you try to again find the vertex which has minimum value. So the min heap although will have uh, v v nodes, but you're going to write the update equation e times because e is the number of edges. Did everyone got this? Or do you want me to explain once more? Everyone please respond so I'll know and I can move forward, or should I explain again? Everyone's writing the same comment. Got it? Okay. See, don't worry. This thing will again come up in Dijkstra's algorithm, okay? Because I told you there's not much difference in prims and Dijkstra's. Okay? Fine. So now let's see what do I mean by Dijkstra's algorithm, okay? So now the application perspective for prims and Dijkstra's are a little different, okay? So what I want to do is I want to solve a simple problem, and the problem is I start with the source and I want to find the minimum distance of that particular vertex from every other edge in the from every other vertex in the graph. This is called single source shortest path problem. Okay, single source shortest path problem. Okay, so remember Dijkstra's is again a greedy algorithm. Okay, it is based on a greedy technique. So your question is given a graph, a problem statement in fact is given a graph and a source vertex in the graph. Find shortest path from that source to all the remaining vertices in the graph. And of course, see, we are talking about simple graphs, so self loops are not allowed. Okay, these are simple graphs. Okay, so below thing that I've written is the update equation that you should remember. Okay, so d of u is the current value, key value of u. D of v is the current key value of v, and if the distance from source till u plus the weight of edge u and v is less than the distance of source from v, that means we are able to reach to V from source in a much less possible distance. So you update the value of dV. Okay. So over here, if this condition is true, you say dV is equal to what? Du plus weight of u comma v. U comma v is the edge u comma v, the edge which attaches u and v. Okay. So let's again take an example to solve single source shortest problem. Let's take a small one. We take 5 vertices. Okay. Now what you do is, let's say the source is given to you as 0. So simple thing is, again you use the same algorithm. You initialize this as 0 and remaining as infinity. Okay. Remaining as infinity. Alright. Now the update equation, please understand the update equation. Update equation is dv is equal to du plus weight of u comma v. Okay. So you are right now at 1. Okay. So from 1, whichever all the vertices which are adjacent to 1, you try and update their key values. Okay. So now 0 plus 5 is less than infinity, correct? So I'll update this to 5. And 0 plus 3 is less than infinity, so I'll update this to 3. Okay. Let me use red for updation. This is 3 and this is 5. Alright. Now you're not selecting any path. Okay. You're not selecting any path. So from here, what is 3. All right. It's not looking good. Okay. So from here, what you do is as simple as that. You pick up the minimum. Okay. Again, you pick up the minimum. 3 is the minimum. Okay. 3 is the minimum. So from 4, you again do the same thing. But the only difference is now when you update for 5 now, you'll include this 3 as well. So 3 plus 2, which is what? 5. So 5 is less than infinity, updated. Okay. Then 3 plus 7 is 10. 10 is less than infinity, updated. Alright. So this is it. All right. So now out of these two, what you'll see the minimum. So this is now 5. Okay, this 5 is done. So we'll actually, oh, sorry, I did not give the vertex for this. Okay, so anyhow, it will not make any change. So because, okay, let me just say this is 1 to make it interesting. One moment. I forgot to mention this, the weight of this edge. So let me say this is 1. Now see, for 4, I have not updated this guy. See, this guy. This guy previously was 5, correct? So now 3 plus 1 is 4. So basically what I'm saying is, if I take this route now, this guy to this guy, this is nothing but 3 plus 1 is 4. So I'm able to reach to 2 with 4 cost rather than a 5 cost. So this means this is equal to 4. Alright? So fine, this is done. And yeah, this is 4. So this will be the minimum. So I'll assign this value as 4. Now from 2 you will again check. So this is 4 plus 6 is 10. And next value is 10 only. So you don't have to really worry. Okay, no need to cancel. And 2 is, rest of the things are done. So now you see, okay, this 5, this has to be processed. So 5 plus 3 is 8, and this is 10, so this is less. Now you'll select 8. Okay, so now this guy is again selected. So now single source shortest path means the key value, which is the final key value for all the nodes, that is the cost which it takes for that particular node to be reached from source. Okay, so I'm just giving you a general idea. This is not the whole algorithm. We need to keep track of other things as well. Okay, is the general idea clear? How we are using the update equation? Previously, update equation was this only. All right. So now what we are going to do is we are actually going to formally do the whole question for Dijkstra's. Okay, formally do it. Formally means I need to take care of few other things as well. All right, so let me try another question now. Okay, so let's say 1, 2, 3, 4, 5, and 6. Okay, okay. This is, let's say, 2, this is 3, and this is 2, and this is 4. Mm, this is 1, 3, 5, and maybe this is 7, and this is 2. All right. Okay, so now with Dijkstra's algorithm, I basic thing is clear, but what we do is we want to keep track of two things. Okay, one is the visited array. Okay, so what we'll do is all these 1, 2, 3, 4, 5, and 6. Okay, for all these 6 nodes, I want to keep a visited array which actually keeps track of which all nodes have I visited till now. Okay, this will keep track of which all nodes have I visited till now. Alright, and the second array is called, you can say, predecessor, or you can say parent also, or predecessor also. So again it will have what, 1, 2, 3, 4, 5, 6. Initially all are null. Okay, all of them are null. Okay, so what you do is, see, if you remember in MST there was no path which was being formed, correct. But in this, if you check now, I was able to form some path like this, correct. I was able to form some path like this, right? 3 plus 2, 5. So you should know from which place to which place I am able to go. Okay. So if I say 5, I can reach 5, I should know the path also, correct? So that path tracking was not available when I solved the problem over here. If I just change the update equation, path information is not available, right? So basically this was 8. How do you reach? How do you reach using cost 8? How do you find that path? They may give you a question. They may say Dijkstra's algorithm is run using this as the source vertex, and then in the output of Dijkstra's algorithm, which is the path you will follow to reach any particular vertex, and they'll give 4 options. Is the question clear to all of you? This is few extra things that we have to do apart from what we did in Prim's algorithm. So I need to keep track of this part, like 1 to 4, 4 to 5, 5 to 3. This is the path which will give me cost 8. So I just don't need the cost, I need the path also. Okay. So this is why we have this predecessor. Okay. So now let me run using this. So again, let me just take blue color. This represents infinity and all right. So let's again run the Dijkstra's algorithm. So between 0 to 3, okay, there are, this becomes what, 3, and this becomes what, 2. All right. So between 2, 3, infinity, 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 which is minimum? 2 is minimum. So what you'll do is, now you are going to see what all updates are made. This is visited 1. Now 2 is also visited because 2 is now in the single source shortest path algorithm. Okay, that is now being the vertex in consideration. Okay, and if you see, the parent of 2 will be what, 1. Is this modification clear? 2 will be 1. Okay, and I've added this vertex to my final answer, this edge to my final answer. All right. So now you are at 2. Now you're going to modify or update the values using 2. Okay. So when you do that, 1 is 3. So this is 2 plus 2, which is 4, which is greater than 3. So no need to modify. Now 2 plus 4 is 6. This is what, infinity. So this will be modified to 6. Fine. And that's what we have. Okay. Now what you do is you just say, okay, so 1, 2, 3. 3 is the minimum here. So I'll basically add this edge and I'll modify this. Okay. So now you'll next visit 3. Okay. And the predecessor, this guy would be what? 1. Okay. Because you have to check the parent of 3. Okay. Or the previous edge of 3. This guy will be 1. All right. Now all you have to do is what? From 3, you have to keep modifying things. The key value of 3, the key value of vertex 3 is 3, and then this 3 plus 3 becomes 6. Okay, and this 3 plus 1 becomes 4. Now this 6 will be modified to 4. All right. Now which is minimum? Minimum is 4, 6, infinity. 4 is minimum. So you will consider this particular edge and you will say the parent of 4 is 3. The parent of 4 is 3 and you will visit 4. All right. Is the algorithm clear so far to everyone? Yeah. Now I'm modifying these two arrays also apart from modifying all the values. So now 4 plus 2 is what? 6. 4 plus 2 is 6. So modify this as 6. Then 4 plus 5 is 9. And this is already 6. This is less than. So I'll not modify it. Okay. So that's all the modification I can do. Now these two are 6. You can do anything. So let's say I want to write this. Okay. So let's fix this now. That means the parent of 5 is 3. Parent of 5 is 3. Okay. And then what we have is 6 is modified, this is 1, and then 6, 7 is 13. So I don't want 13. 13 is actually greater than 6. So from 4 you start, 4 to 6. You draw this line. Okay. So 4's parent is what? Sixth parent is what? 4, and 6 is also visited. Okay, everything is done. So this is my values. Okay, so the nodes, the values which are there inside the nodes, those will represent cost to reach that node from the source. And now let's say I tell you, tell me the path from which I will reach 6. Okay, so what you do is you just visit the parent array. So 6, 4, from 4 to 3, 3 to 1. So 6 to 4, 4 to 3, 3 to 1. Is this clear? And are you clear about the usage of parent array now? How do you use parent array? So again, so see, I have written this algorithm. This the source for this algorithm is Geeks for Geeks. Okay, but I'm not going through the algorithm. This is very big. Okay, so I've just written for you guys so that you know that okay, this algorithm is included in your notes. Okay, so only I'll go through the important points. All you do is this is all initialization happening. Okay, you pick up the vertex which has minimum distance that we know, include that in U, and then update the distance value. Okay, now update equation is what that I mentioned, right? That is distance, that is sum of distance of U and the weight edge. If this is less than the distance of V, then you update the distance of V to this, otherwise you keep it as it is. Okay, so basically, always you want to reach with less cost. So if you are able to get some less cost, then you are good to go. Okay. So now just try this algorithm. Just try to solve your single source shortest path for this algorithm. Okay. For this vertex, I'll say. Let me just do one thing. Yeah. Okay. Now do it. Try this. Please make sure you maintain visited array and parent array, both the things that we have discussed. Anyone else who completed this? Please make sure to maintain parent array, because they can give you this question that what is the path from the source to a particular vertex in the single source shortest path problem, if you solve it by Dijkstra's algorithm. Anyone who needs more time, or can I discuss this problem? Okay, okay. Gayatri, Aditi, Kajol, what about you people? Neha, have you completed? All right, so let's discuss this problem now. Again, the same thing we have to do. Again, I'll take this visited array, which I have for 1, 2, 3, 4, and 5. Okay, and let me take your parent array also, 1, 2, 3, 4, and 5. Okay, right now the values over here are 0, and this is not visited. Okay, so you'll visit 1. Okay, from 1 you have to check, okay, these are all infinities and infinity. Okay, fine. So now from 1, the cost of going to 2 is what? 0 plus 5, which is what? 5. And cost of going from 1 to 3 is what? 0 plus 9, which is 9. So this is modified, right? Now you have to find the minimum. So 5 will be the minimum. So you will visit 2 then, and you modify. You include this guy in the vertex, in your single shortest path, and the parent of 2 would be 1. Okay, so basically this way is the graphical way. Okay, but in the computer, if you try and code, this is how you'll this parent array you'll use to find the path. That's why I'm telling you to maintain this. Okay, when you implement this in a computer using C language or any other language, you'll use the parent array to check the path for everything. All right, so from 2 you have to modify now. So from 2, cost of going to 3 is 5 plus 3, which is 13. So this is greater than 9. So we have a cheaper cost already. Good. Okay, so from 2 going till 4, the cost is what? 5 plus 7, which is 12. So I'll modify this as 12. Done. Now you see 9, 12, and infinity. So now 9 is what? The minimum guy. Okay, so you make this as visited 1, and this is connected now, and you make parent of 3 as 1. All right, so now from 9 going to 4 is 9 plus 3, which is 12. So 12 is already there, so no need to modify. From 5, 9 plus 2 is 5, 11. Okay, so infinity changes to 11. All right, now you have what? 12 and 11. Okay, so we'll modify this first. Okay, we'll actually consider this first. So this is 1, and now your parent of 5 is what? 3, and this edge is selected. Your parent of 5 is 3, and this edge is selected. Now from 5 you have to go till 4. So that is 11 plus 6, which is 17, and we already have a less cost, so we'll not modify. All right, so that means the last one will be this node. Okay, this node will be what? 5 plus 7, right? So this node will be visited, and the parent of this guy will be what? 5, 2. Okay. And one more thing, I think a small change in the algorithm, a small change in the algorithm. So basically, when you modify the parent now, whenever you modify this guy, okay, then only you modify the parent. Okay, then only you modify the parent. Is this point clear? So whenever from infinity I modified it to 5, so then only you modify the parent to 1. Okay, because after that we'll lose track of which edge was used to modify this cost value. Is this point clear? Okay, so something like this will happen in the code. So when you do d of v is equal to d of u plus weight of u comma v, you say the parent of v is nothing but u. Is this clear? These are to be done parallelly. While solving, that's all right, but when you code it, everyone, is this clear? Yes or no? So but just take care of this small modification. Okay. All right. So this is how you're going to solve the problem, and this is the solution that I've shared. I think we have this on this slide. Right, so this is the solution for it. Okay, so now let's end the session here for today. Okay, and in the next class what we are going to do is we are going to look at few more problems of Dijkstra's algorithm, and we'll discuss the time complexity as well and some improvements on that. Okay, and we'll see some drawbacks, I mean some cases where Dijkstra's algorithm will not work and which leads to Bellman-Ford. Okay, so in next class, that is I think Sunday, we have Sunday morning. Yeah, so Sunday morning we have class, and the class will start around 9:45. Okay, guys, it will start from 9:45 to 11:45 a.m. in the morning. Okay, so this is when the class is there. And one more thing, once I complete Bellman-Ford algorithm, that is the end of greedy algorithms. So after that, we'll try to solve some gate problems which have come in the past. Okay. And once I solve the gate problems, then you'll have dynamic programming. All right. So any questions that you want to ask? All right. Okay. So, okay. So thank you everyone for joining. All right. Okay. So let's start the session for today. So we looked at a lot of greedy techniques and I mean, problems which can be solved by some greedy technique in the previous class. So today we are going to discuss how you can apply. There are some problems actually in greedy algorithms which can be actually in graph algorithms, I'll say, which can be solved using greedy technique. Okay. So before we discuss any such algorithm, I would like to introduce what do I mean by a spanning tree and a minimum spanning tree. All right. So this is the topic for today. So a spanning tree is something. So suppose a graph is given to me. Okay. Suppose I have a graph. Okay. And assuming that it is connected as well as it is undirected. Okay, undirected connected graph is given to me. All right, so if I try to create a subgraph out of it, okay, this subgraph has all the vertices of the directed graph and is connected. Okay, it has all the vertices of the original graph and it is connected. Okay. So this subgraph is known as a spanning tree if this subgraph has n minus 1 edges. Okay, n minus 1 edges. Okay, so let me take an example, something like this. So if I have a graph, let's say 3, 4, 5, 6, something like this I have. Okay, so if I want to create a spanning tree out of it, just a minute. If I want to create a spanning tree out of it, it will be nothing but you keep all the vertices of the original graph and try to use n minus 1 edges to create the spanning tree. So something like this, and let's say this, and then this, and then this. This is one of the spanning trees, okay? So those n minus 1 edges are to be taken from the edges of the original graph, okay? That is why we are saying that this is a subgraph of the original graph. That means the edges which are present in the subgraph should be, of course, present in the original graph, okay? So this is what is known as a spanning tree. So if I look at the definition now, a spanning tree is a subgraph of a connected and undirected graph, which is a tree, of course, and is connected and connect, sorry, not connected, connect all the vertices together. Okay. The number of edges, if a graph has n vertices, original graph has n vertices, number of edges in the spanning tree would be n minus 1. Okay. This would be the number of edges in a spanning tree. Okay. So now based on this, let's see what is a minimum spanning tree. So minimum spanning tree is basically a weighted connected. So right now I took this graph. This was unweighted. Unweighted means there's no weight on each edge. So by default you can assume same weights. Like you can